Tony Rome. I'm the Senior Associate Dean for Research at the School of Medicine and the Associate Director of the California Nanosystems Institute. And it's my pleasure to be able to introduce our Biobasics seminar series and thank the people that made this event possible. The Research Administrators Campus Committee, better known as the RAC, is a wonderful asset to the School of Medicine, and they are our co-sponsors for this event. And if you're interested in this committee, the RAC chair, Cherry Novar, is the person to talk to. The development office also has helped us put the series together, and Zoe Cotton from development helped us begin the biobasics concept. Also, Marcia Smith and the folks at ORA are also instrumental in helping make this series a success. Of course, I have to thank my team in the Dean's office, Dion Baybridge, Rosalie Encarnacion, and others who also help out make this possible. So it's really a pleasure today for me to be able to introduce my friend Andre Nell, whose seminar today will be on nanotechnology and nanomedicine. This is, of course, a topic that is very near and dear to my heart. Dr. Nell is the chief and founder of a division of the Department of Medicine called the Division of Nanomedicine, something that doesn't exist in most medical schools, maybe in any other medical. He's also the director of a new center that's housed in the CNSI called the University of California Center for the Environmental Impacts of Nanotechnology, or CEN. He directs the University of California's Nanotoxicology Research Training Program as well. He's a very busy guy, amazing scientist. His awards, honors, associations, membership, and his CV takes up, so I'm going to actually read the whole thing to you.
Please not letting.
He just got back from a conference in Moscow, which was where he co-chaired the U.S. Technology Working Group on Nanotechnology, Environmental Health and Safety. So it's great to have him here at UCLA. I'll say finally, we always go on and Google the person to get some dirt on him. We find out when we Google Andre that he's a famous cricket player. The guy's a little bit younger than Andre, and Andre doesn't want his reputation. It's really very questionable. But when you go through the pictures, you have to go through 19 pictures of this other Andre Nell before you hit number 20, which is our number. But it really gives me great pleasure to introduce him today. Oh, and one more thing, I find out from the web that he's a qualified flight medical officer ranked as captain of the South African Air Force. Is that you, Andre? Good. So help me welcome Andre.
Well, it's a pleasure to speak to you today about nanotechnology and nanomedicine. I first want to thank Lenny and the organizers of RAC for inviting me to speak. I will be saying a little bit towards the end of our appreciation of the importance of our administration at UCLA. A machine is only as good as its organizing parts, and in the nanotechnology ventures that we have at UCLA, I'm very fortunate to work with outstanding people. I cannot tell you, I'm at the process of submitting my annual report for this center at the bottom, and to have the type of admin support that David Avery and his team is providing is, I would not be able to do this job without them. So without further ado, let me tell you quickly, and I'm trying to make it picturesque, and I realize that a lot of the concepts are sort of deep physics, chemistry, mathematics, so I'll try and make it as picturesque as possible. If I go too fast, please pick up your hand. I'll just say that where nanotechnology comes from is a progressive human endeavor over the last 70 years or so of recognizing that we can make objects that perform functions for industry commercialization that began in the micron range, and by micron we talk about sizes that is bigger than 1 millimeter in size. There's 1 millimeter in size and below, so that's about the size of a pinhead. And it progressively became smaller and smaller and smaller until we hit this part here of about 0.1 micron. I'll explain to you what that means in a moment, or 100 nanometers, where we could achieve not only smaller objects but new functions. Simultaneously, a movement began, sparked by some ideas that was first put forward in 1960 about also building highly functional materials and commercialization from the atom, from the atomic level up. So the atom is down here at this level, very, very small, 0.1 nanometer, also known as 10 angstrom. And progressively through the last 20 years, and especially in the last 10 years, through building through the atom up, we also got into the nano world. And the whole idea about the nano world is creation of new systems that I will explain to you. So what is nanoscale? The easiest explanation that you read in newspapers and the popular scientific press is that nanoscale is about 1/10,000th the width of a human hair. So I've decided to show you a picture of a human hair and with a carbon nanofiber wrapped around the hair. Okay? At another level, we get a little bit more technical. Here is a scale of nanometers, of which a tennis ball is about 10 to the 8 nanometers, and to put that into popular jargon, that is 100 million nanometers. Okay? That's a number that is so obscure that it is difficult to even understand. But nano begins in this area of objects, so atoms are in this scale, and nano begins from about 100 nanometers down to the size of 1 nanometer. Here is where nanoparticles, nano devices are being built. And if you compare that to common concepts, a virus exists sort of at the upper limit of this nanoscale. Bacteria are 10 times larger, and cells such as cancer cells is 100 times larger than where the nano begins. And to put that for you in proper perspective, I now show you a cancer cell. This is a human white blood cell. I got this picture from Lenny Rome. Changed the format somewhat over time. So here is a cell, a white blood cell, and here is its nucleus, and this is the total cell, and its width is about 10,000 nanometers. And embedded in this, I show you 100 nanometer nanoparticles so that you can sort of see what the scale comparison is. And why I'm showing you a nanoparticle embedded into a cell is also because what I'm going to show you in the nanomedicine part of the talk is we want this particle to enter the cell and to work, to perform new functions. And the advent of this technology is going to change medicine forever based on the ability to take a small package into a cell to perform functions such as we have never seen before. Okay? So nanotechnology have two concepts. So this is very technical, but let me try to explain you. The two things are small, nano-length scale, and function. And you cannot separate the two. As you scale down from the micron size level to the upper limit here of the nano world, something amazing happens. materials change their properties from things that we understand as bulk material properties, and I'll show you gold as an example at the moment, where as you scale down, the material achieves new surface functions. It can perform new feats of chemistry, physics, and biology. And at the same time, this is made possible by the molecules or atom inside the material. Instead of being locked inside, everything goes to, most of the material of the atoms goes to the top. So you get a progressive increase in the number of molecules at the surface. So the small size and a surface that can work is what the nano revolution is all about. And let me explain that by way of gold. So we all understand. Can you just see? Okay. The animation didn't work, but anyway, the bulk material that we all understand, the properties of gold, used as bullion, used as jewelry, but when we bring the gold down to 100 nanometer scale, cut it smaller and smaller and smaller, it all of a sudden changes. It is no longer just gold. In this world, between 100 nanometers or 1 nanometer, it gets new electronic, optic, magnetic, energy, and quantum mechanical properties. And what are those properties? Well, if I take the gold particles that you know, and I begin down here with a 100 nanometer gold particle and make it smaller and smaller, this up. I think it is locked in this. Okay, be careful. As we go from 100 down to 5 nanometer particles, the gold attains all the colors of the rainbow. So the explanation for this is given here. If I take the 5 nanometer particle and I have an incident light beam, the reflection properties, the quantum effect of this particle is to take that light and reflect it back as a pink color or a red color. So we're out on the smaller end of the scale. If I take a 30 nanometer particle and I have an incident light beam, it reflects back a blue color. So we cover the full spectrum. And at the insert, you see the painted, a picture of a painted church window in Europe. A lot of those beautiful, brilliant colors are all made by artists of that age, having figured out, without knowing about nano, to make colloidal gold suspensions of different size materials and achieve all this functionality. What is nano? Another example for you. You write with your pencil and a piece of paper, you get graphite, which is basically the chicken wire that you see here. You have a single layer of this graphite, you can actually win a Nobel Prize. This happened in 2010. But anyway, so you now take this graphite and you cut a rectangle along this chicken wire and you roll it up into a circle. If it is bigger than 50 nanometers, this whole, under the law of physics, this whole structure will collapse and you will then have chicken wire. But if you make it smaller than 50 nanometers, something amazing happens. This is no longer graphite. Instead, what you now have is an object called a carbon nanotube. And this carbon nanotube is 100 times stronger than steel, but 10 times lighter. It can be an electron conductor, and it can carry more than 1,000 times the current of a copper wire. So we'll get back to that, but just think about that. If you make a material that is stronger than steel, lighter, and a better conductor, I'll show you the utility in a moment. Finally, to understand nano, let's talk about this size and surface area effect. So let's take a material such as zirconia. And we say we cut a 1 centimeter cube. There's 6 different sides, each 1 square centimeter. The total surface area is 6 square centimeters. If you shine light on that zirconium crystal, you'll be able to get enough light on your desktop to be able to read a book. If you now take the same amount of material, same amount of atoms, you cut it into 1 millimeter cubes, it now has a total surface area of 60 square centimeters. If you can light up a room with a reflection. If you take the same and you cut it into 1 nanometer cubes and you shine light, you have a total surface area of 60 million square centimeters. You can light up a football stadium. Right? That's the same material. So how are nanomaterials made? So based on what I've now shown you, in order to get into this nano world, you could either have a top-down process where you take bulk materials and you break them down into smaller units. And this is typically performed on solids or solid materials, as you can imagine. And the other process, the one that is actually carrying most of the nano revolution, is the bottom-up process where you begin with materials 1 atom at a time or 1 molecule at a time. And you reconstruct them so that they form objects that you want to create, typically done in gas and liquid phases. And out of the ability to use the elements in the periodic table, you can build all these nanostructures, from spheres to rods, from wires, tubes, etc. Now you have tiny objects with new principles from which you can construct new materials. And as a result, what we are seeing is the emergence of a powerful new technology that is going to change our commercial processes and consumer products forever. It is going to introduce, as examples of what are already becoming available, stain-free clothes, self-cleaning glass, new types of building materials, electronics, motor vehicle and aircraft components, and then a lot of stuff in the field of medicine that I will review for you. So let me show you one example of a used material. So this is the Beijing Opera House. It is next to Tiananmen Square. We saw it around here. It has a huge glass dome which never had to be cleaned. And the secret behind this glass is that the whole surface is made up of glass on which people absorb tiny little nanoparticles made out of a material called titanium dioxide. It is the nanomaterial at the moment that is produced in the largest amount worldwide. And this nano-titanium oxide particles is studied on the surface of the glass. And when light comes in, this material has, again in the deep scientific concepts, the property of a semiconductor, which basically means that it takes the UV light and it creates an electron that jumps up to very high energy levels, and it leaves behind in the pocket a hole. And then the electron and this hole chase each other around, and then when they come into contact with the surface of the particle, They either give the electron to material that collect on top of the glass, or they take an electron, and that is they perform a very powerful oxidation reduction reaction that can rip apart any dirt or organic material, and therefore the window is self-cleaning. To give you another example, so I told you about the carbon nanotubes. So here is what they look like under a high-resolution electron microscope. And when this began, these materials, I already told you, have these amazing properties, 100 times stronger than steel, 10 times lighter, better conductivity. But as recent as 5 years ago, we could make them, but we could not yet assemble them into consumer products. And it was absolutely amazing that through American ingenuity, this company called Nanocom, led by Peter Hunter, who gave me the slide, they became the American Rumpelstiltskin. They were able to develop the technology to weave these fibers together. And not only weave them together, but develop an automated process where they could make kilometer rolls of carbon nanotube wires, and they could make kilometers long sheets of carbon nanotube sheets. So now you have something incredibly amazing, because if you take these carbon nanotube sheets, you can make the aircraft body and make it 10 times lighter. You can replace all the copper on board, which is 8,000 pounds of cable. There's a saving of $20,000 operating cost for each pound that you reduce the aircraft weight. And so you can imagine the impact that this is going to have on consumer products. So as in one example is what it will do to the car industry, where through the principles of nanotechnology, we will build batteries and energy storage out of nanomaterials. The lithium batteries already are nanoscale electron transducers. We will be able to make the body from carbon nanotubes, so-called composites, and make them lighter. We'll make the wheels turn easier with less lubrication needed, and with resistance rolling tires that have superior resistance. These tires will last longer, and we will have a whole bunch of gadgets on top that will make this car a totally new consumer product with new properties. And all the stuff that I'm telling you now may have sounded like science fiction 10 years ago. I will show you in a moment that I've been on this national panel where we just reviewed what happened in the last 10 years and also wrote a book about what will happen in the next 10 years. And so this is all actualization that will come about in the foreseeable future. And how important is this going to be? Well, important enough that in spite of all the recessions that has hit the world, nanotechnology has grown 25%, doubling every 3 years, and will achieve by 2020 a market value of $3 trillion. And if you want to compare that to our federal budget, which for 2010 was 3.4, of which we collect from taxpayers 2.1, and that shortfall, of course, is the basis of a lot of pain and problems. So you think about a technology that could have the magnitude to replace the entire U.S. federal budget. You can understand why the U.S., Europe, China, Japan, Singapore, Russia are all backing on this technology as a major source of revenue production, and, as I will explain, probably also a major source of sustainable living. So with that background, let me introduce you to biology. So also amazingly, in the last 10 years, we discovered, although we knew proteins and nucleic acids, that a lot of the molecules of life exhibit nanoscale features, and therefore function on the principle of having a big surface area and atoms that can interact. So a lot of the biology and the life processes are based on nanoscale functions. And for instance, in the mitochondria, we've come to appreciate that in order to produce energy for the cell, the electron transduction complexes that make ATP all have nanoscale crystal features in order to do this transduction. So nature has figured this out. And has given us now the ultimate toolbox that if we make an engineered nanomaterial with all its atoms on the surface, we can indeed create an environment where we can let the biology atom by atom interact with a nanoscale object that is man-made and install new functions. And so what are these functions? Well, so let me first give you then a definition of nanomedicine. And I've simplified it. It is the design and synthesis of nanoscale systems that enable biomedical technology advances by making use of significant nanoscale systems that hold advantages over traditional methods of imaging, diagnosis, and treatment. So the pillars of nanomedicine is materials and devices that can diagnose, image, deliver drugs. It can image and deliver a concept that is known as theranostics, and it can change regenerative medicine and tissue repair, leading already to point of care, improved diagnosis, imaging, and treatment, and then underlying all of this with the advent of anything that's a powerful new technology, the requirement to do it safe and to do it sustainable. So I'll say a little bit about that. So the big breakthrough area in which the National Cancer Institute is actually considering nanotechnology as a major framework that will change cancer therapy in a major way in the next 10 years. And the US is at the lead of this development in nanomedicine. Making use of nanotechnology in one context is that cancer, when you can cut it away, as we often see with surgeons, you can irradiate it, but at its basic level, it is a disease of a cell. And nanotechnology allows you now to take care of the disease at cellular level by trapping drugs inside the particle, send the particle to the cancer site, and allow the drug to be released at the cancer site so that a lot of normal tissues are relatively spared. And I say I want to make the relatively spared. About 5 years ago, everybody promised that they're going to make a magic bullet that is totally only going to target cancer. That is not true, the way that physiology works. But I'll show you how we make use of the concepts to make the nanomaterials. So the practical use then is to take a cell and to make use of a nanocarrier in which you can put a drug and then make use of uptake channels inside the cell to get the material in, and then inside the cell figure out in its different compartments to release that material so that the entire delivery is towards the cancer cell and inside the cancer cell in order to perform the functions. So let me show you as an example. I'll explain in a moment how we make these from the atom up. My colleague and friend, Dr. Jeff Zink, makes us these silicon nanoparticles. We make them as circles, spheres. We also make them as rods with different lengths, short, intermediary, and long lengths. And if you take these rods and you bring them into contact with a cancer, and this is a human squamous carcinoma cancer cell from a patient that died from cervical cancer, and you bring the spheres to this nanoparticle, its surface remains relatively inactive. But if you bring rods here, look what happens to this surface. it becomes highly interactive, starts seeing this shape, and all of these particles are wrapped inside the cell in huge, huge numbers. And where they wrap in, the cell actually makes use of a mechanism. So here are the particles, where it puts out a little piece of a surface membrane that wraps around those particles and then entrap them inside the cell. And this is an active surface sensing a nanomaterial context and making use of that context to take the particle into the cell. And this whole piece of biology as done by Meng Wan and Min Zhu in the California Nanosystem Institute is premised on the fact that a cell has a wiring system at its surface made of a structure called actin, and this actin normally lies flat at the surface, but when you present it with these rods, the actin stands away from the surface and makes those little projections that take in the particle. And this is a bilateral communication system that you can tune and use to get the material inside the cell. So how do we make these materials? So again, through the ingenuity of nanochemistry here at UCLA, in particular Jeff Zink's laboratory, Jeff has developed from the atom up a way to make these silica particles, and not just to make them as little round objects, but to make them as little round or rod-shaped objects that are full of holes, right? Glass bubbles. And from the atom up, the process worked by first making a detergent. That is basically what you use for washing your body, soap. And then you have this detergent making a object that we know is a micelle, and you assemble these micelles into penny rolls, and then if you take these penny rolls and you dip them into a solution where you instill atomic level cross-linking of the silica, they will harden around these stacks, and then if you finally have the glass bubbles and you wash them in an organic solvent, you wash out all the penny roll material, and what you stay behind with is a particle with a massive surface area, huge packaging space in which you can put drug, and it is all done at nanoscale. In fact, you take 100 milligram of these particles, a pinch of salt. Its surface area is so big it will cover a football field. Okay? And what can you do with it? Well, now you can take drugs, cancer drugs. And you can, as a prime example, you can take this cancer drug called camptothecin that comes from the Camptotheca tree in Asia. It's a highly potent cancer drug, but unfortunately very toxic. And toxic because it fails to stay in solution. If you inject it in the blood stream, water makes the material clump together and it creates a lot of toxicity. But if you now take these nanoparticles with their huge surface area and interior packaging space, and you take the drug and you soak it into the particle and then wash the particle, you are able to now have the drug go and hide out in the pores of these particles. And then you can take the particles and put them into water, into blood, and they will stay in solution. And as an example of the efficiency of this, if you grow a lawn of cancer cells, this is pancreatic cancer cells, these particles now go into some of those uptake mechanisms that I've just shown you, where the cell wraps in a little vesicle. And you can see here the drug, which is in this case it's stained green, it sits inside this little vesicle. And if you look at the depth in the cancer cells, 100% remains alive if you have the camptothecin in water, because most of it becomes insoluble and drops out of solution. But if you put this in the pores, you can kill 100% of the cancer cell with the same dose. And what can you do with that? Well, next step is you can go into what we do in the California Nanosystems Institute. Again, this is the work in collaboration with Jeff Zink. carried out by Meng Wan and Menzu, Shanzi, and the idea here is we take human cancers, because that's what we want to ultimately cure. We make the cancer, we put a little gene in them that is the firefly luciferase gene. So literally the tumor lights up with a little pocket of light. You can then use an imaging equipment in the Crump Institute to show you where this cancer grows under the skin of a mouse. There's the cancer growing. And now you can target to the cancer nanoparticles that are labeled with infrared, a tag that we can put on them because we can pull that into their structure and we can image the particles as well. And to treat the cancer, get the drug to the cancer site, we're making use of a principle that most cancers have abnormal leaking of its blood vessels as compared to normal blood vessels where you don't have these big leaks between its barriers. So the particle can leak past these abnormal barriers, get inside the cancer, and then get inside the cancer cells. But in order to achieve this outcome, very important, you cannot make a particle that is too big for these fenestrations, otherwise it will just remain in the circulation. In fact, you've got to make them so that they can be small enough to leak across into the tumor. So again, through ingenious design, you can tune all these principles from the atom up. So when originally we began with a human cancer growing under the skin of a mouse, we injected these particles. Now all the colors here have changed, but you will be able to appreciate most of the particles went to this organ here, the liver and the spleen. You can see they have the most intense staining. And in fact, if you sacrifice the animals and you go and look where those particles are, in fact, that's the liver, and that's some go to the lung, and that's the spleen, and very little got to the tumor. You see no color there. And the reason is that what happened, the size was 130 nanometers. The tumor size prefers close to 100 nanometers to slip across that border. And also the particles clump together. So if you look here in the solution that you hold up against the air, you can see they all look like a sort of a cloudy solution. And why is it cloudy? Is because these particles in the blood tend to stick or clump together. So they're too big. They didn't get in. Right? Now we have to find solutions. And the solution is, number one, is to make the particle smaller. We made it now 50 nanometers in size. And we prevented clumping by decorating its surface with a polymer. A polymer is basically a little nano structure that is stringy in nature and it stands away from the surface. It sits there like decorating almost like hairs. And you can make the polymer give it a charge so that it will repel each other and that the particles now will fail to clump together. And the polymer also prevents the particles from everything being taken up by the liver and spleen immediately. And if you go back now, and you look at the outcome, you will now see in the imaging of the animal, unfortunately the colors got changed, but you now have a huge amount of particles going into the site of the tumor. And if you now, the solution becomes clear, you can hold it against the light, it remains sort of in the bloodstream, and it can get into the liver, into the spleen, still remains active. That is the one of the lies that we're told in Nano, that you can totally target it. No, that's not true. But what we can now do is we can get up to 15% of these particles inside the cancer. And if you look at what happens to the cancer, so all the colors got changed, but basically here is the size of the cancer in 5 different animals. If we inject them at weekly intervals with empty particles, the cancer still grows at the same rate. If we inject the free chemotherapeutic agent, we shrink them, but not find much. And the animals also develop huge side effects. They lose weight, they become sick, they don't look well. If instead we put the drug inside the nanoparticle, we shrink considerably the tumors, and if we go more injections, the tumors disappear. And it disappears with this huge safety feature. So here is the weight of the animals as a sense of the well-being. As you see, the free cancer drug. That's why patients also get as sick as they do. You give them cancer chemotherapy. So every time you inject, you get a huge drop in the weight. But if you put the cancer drug in the particle, there's no weight loss. The liver enzymes don't go up. And you theoretically have the chance of achieving a cure. So with that, I then covered nanoparticles in therapy, and I will also just say that what I'm showing you now is just an example of what's done here at UCLA, but we have a host of nanoparticles that are emerging for doing drug delivery. They have all sorts of different names. I'm not going to go through the names, but I do want you to recognize the bolts that Dr. Lenny Rohn make here. That is actually a cellular nanostructure that his group is developing for cancer therapy, and I'm sure Lenny probably have given you a talk about the amazing result that they achieved with this. So now I want to show you one example of an intelligent material surface for regenerative medicine. So we're in the era of stem cell therapy. We're in the era of recognizing that we can patch tissues and organs, that we can prolong life. What I'm going to show you here is to patch heart tissue by making use again of a polymer that has temperature sensitive behavior. And this polymer, in its temperature sensitivity, in one form, it absolutely repels water so that the whole material stands away from the water surface. And in another form, it's in one form it is water repelling and it stands away from the surface. In another form, as you change the temperature, it soaks into the solution and it attracts water. Okay, so let me show you an example here. So what we have is an intelligent surface, and this surface I'm going to coat first with this polymer at 37. It's hydrophobic and it all falls flat. So I lower the temperature, it all stands up. Okay, now what can you do with it? Well, so you now coat in a tissue culture dish the polymer at 37 degrees, and you put in cells, in this case cardiomyocytes. All the cells grow on this surface because they love a water repellent surface. And not only do they grow, but if you drop the temperature to 20 degrees, the whole cell sheet comes off with its basic, we call it extracellular matrix, intact. One of the big reasons why we cannot use cell therapy to patch and repair is because if you take the cells off a tissue culture dish, you lose the extracellular matrix. Here is an instance through cell sheet engineering where it remains intact. And if you now look at that group of cardiomyocytes that is grown, they not only assemble, but the extracellular matrix also allow them to contract. So the whole sheet of cells work like a intact organ. And if you stack a couple of these sheets on top of each other, because the extracellular matrix will allow you to do that, it will act as glue, you have a whole beating cardiac segment, right? You now take a patient that had a heart attack, and this is real. This is what we picked up on this tour that we did around the world to write this report for the U.S. government. A patient who had undergone a myocardial infarct, a heart attack. You can see this segment of the heart is dead. It won't beat. And if you now take the cell sheet, so here is the dead segment, there's all this white tissue. Here is the segment of the implanted tissue, and what you now have is an effective contraction of that part of the heart that will not normally contract. So in this case, it saved the patient from a cardiac transplant for which there was no donor. And in actual real life, he walked out of the hospital. And not only have Dr. Ocano and his group figured out how to use this technology, but they can now do CT scanning of a whole heart and then take all the sections and grow cell sheets for each section and then stick them together, and they are making busy with the technology to replace a whole human heart. Okay. So finally, tell you about, as this panel of experts where we've published this book on nanotechnology research direction for societal needs. And we were fortunate that our UCLA center had at least 5 of the chapters that were written by members of our center, taking a future look in what is going to become a very useful feature. Now, what I want to tell you about nanotechnology, in addition to what I told you so far, is that nano is also coming around at the era where we need sustainability. Okay? We have global warming, we have collapse of our financial systems around the world, we face energy deficits for which there are no alternatives other than to try and build nuclear power stations or make use of wind energy and a little bit of solar fuel energy, but not enough to sustain the world. In fact, if you look at it at a comparable scale, when the previous industrial revolution happened, when James Watt's invention came along, he could not have foreseen from a sustainability viewpoint that this is going to spark a technology which ultimately will be solved by fossil fuel combustion product, oil. And then with oil, the concurrent expansion of human population that is absolute duplicate of what happened in oil, with global emissions leading to where we stand with global warming. And the picture actually gets even more complicated. So we are here at the moment. Oil, if you really sit in these councils where the president's advisors, including Stephen Cho, discusses in great detail what is happening, oil has peaked in 2007 and will never come back. The human population will grow to 9 billion. Currently, human use of fuel versus electricity in green here is about, fuel is about 60% of energy, electricity is 40%. Electricity is not a source, electricity is a commodity, so we need to find a source. And by the year 2050, with the world's expanding population, fossil fuels will only contribute about 10 to 15% of the energy. Wind and solar cells will contribute this amount, and the shortfall will be an amazing amount of 15 terawatt. That's a number, but let me explain to you that the current energy needs of the world, the entire energy needs, is 13 terawatt at the moment. And if nothing emerges in the picture that we have in front of us, we are going to have a lot more problems than we currently face. Now, I think that when we look back one day, if the history is written, we already know the sun is the singular solution to our future energy needs, and nanotechnology is very likely going to be playing a critical role in solving that. And as one example, you can have solar electric, solar fuel, and solar thermal. These are all this concept I may explain to you. But these silica nanowires embedded and can trap sunlight, can have a huge absorption area to capture electrons to make electrons, to store them, and to be able to fulfill this need. And to the extent that here is a sort of a, unfortunately the picture here is somewhat obscure, but this is a new solar thermal instrumentation that is currently being built. And in the Sahara Desert, there is advanced plans that they will put this with turbines to generate most of Europe's electricity. This probably will happen, but we can already tell you that in order to put structures of this size on Earth is soon going to run out of space, and California PG&E already is starting to look at structures that will go up and extend into the sky. So this is already where planning is taking place. So in my final 2 slides, I will be saying something else about sustainability. As we introduce these powerful new materials on Earth, we are faced with their safety assessment. And you can imagine that from what I've shown you now, that nanomaterials do potentially pose a hazard, and you have to deal with that hazard. The University of California Center for the Environmental Impact of Nanotechnology was then created after a competition between US 180 universities competed for 1 year, and finally we emerged as the winner. And the idea by which we won and implemented the research was to say, well, it's going to be impossible to take each of these materials as they're being produced and put them through their paces in terms of safety assessment in higher animals. There's not enough animals in the world to test all the different combinations. That a lot of the research needs to be carried out at the level of molecules and cell to make predictions, and then we feed it back into these animal systems. And I'll show you just one example of such prediction, where we use a series of metal oxide nanoparticles. We make use of screening systems in cells that is being carried out by robotic equipment in the California Nanosystems Institute, so-called high throughput screening, where we can analyze and generate 100,000 assessment points in 1 day. This information as published and work that undertaken by Sajid George, Chanzi in the lab, and many others have then led to be able to make predictions that can come from a computer based on the high throughput that tell you what is potentially more dangerous. This one screen, what was potentially more dangerous was zinc oxide. The second highest, I said titanium dioxide, the most voluminous material being produced. Zinc oxide is the second most voluminous material being produced. We use it on sunscreens, and these sunscreens can potentially wash up and get into contact with the environment. The screen clearly confirmed that zinc oxide has potential toxicity, and that the reason is that it releases zinc ions. And then we could use this information to go back, re-engineer with, in collaboration with Dr. Lutz Madler in Germany, one of our center collaborators, a zinc oxide that is safer. It doesn't dissolve as fast. The predictions when we carried it through to all these animals in the environment was that in zebrafish, the original particles interfered in their hatching. This is a normal embryo, but if you put the zinc there, they roll up and they won't hatch. And then ultimately they don't feed and they die. But if you do the same experiment now with the safer zinc oxide, the hatching takes place. And if you do more complicated experiments in animal and in rodents, you can also see that there is a safety margin to this. So the work that is being carried out then between UCLA, UC Santa Barbara, is a whole host of different sentinel organisms that we choose in freshwater, seawater, and land-based life forms, which we test through this approach of first using what is lower down on the chain and then going higher up. where you can make fewer observations, so you already have to organize your knowledge. And what I can show you here, so here's phytoplankton. And what came out of this work is that phytoplankton absorb nanoparticles. Here is the phytoplankton. Here is the nanoparticle, and the moment that nanoparticle sits on the phytoplankton surface, it starts acting like a spare battery. It starts kicking electrons into the surface of the phytoplankton. Normally, the phytoplankton makes use of sunlight to proliferate and do its job, and by the way, when it does, the process here is photosynthesis, and the photosynthesis fixes carbon dioxide, which is the thing that causes global warming. And then the amazing discovery is that when Mount Manitoba erupted, that was the first time in 100 years of record when Earth temperature went sideways for a while. The temperature didn't go up. And one of the apparent contributions was made that the volcano spewed so much of these iron oxide particles into the oceans that the phytoplankton, which is the biggest biomass on Earth, you can actually see, this is a satellite view, fixed CO2 to the extent that global warming went down. So this is a concept known as geochemistry, and in a recent US Today, they had a whole little special section on geochemistry, and you can go and read that. So finally, it remains for me to then again acknowledge the very important contribution of our administrative staff at UCLA. I think that if it is not for a good administration of science, that UCLA will not be able to occupy the role that it does nationally. From my own laboratory, I've tried to call out the names as we went along, but I want you to just look at the long list of names here. I'm not going to go through the list. And then a long list of very valuable contributors. So let me tell you that what happened with the establishment of this center is we've created a multidisciplinary enterprise between 7 different sciences to interact to do this at a scale that has not happened before. And I think that we therefore have demonstrated what I think will become more and more of a national trend, is the importance of multidisciplinary science. You may be smart, but you can never have the full body of knowledge that is required. Somebody else always has something else to contribute. And I will leave that to the younger members in our audience, where I think this is the advent of how I think science will be driven in the future. Thank you very much.